Hello all and welcome to this next session of the course Pre-Business School Statistics or Pre-MBA Statistics. So again we are sitting in the second week and this entire week has been throughout been about probability, random variables. Okay, so if you vaguely remember the last session we sort of rushed through number of ideas there such as PDF, PMF, CDF, right? And towards the end we talked very briefly about expectation, variance. So again, like I said, these are some summary measures or summary rather important measures to quantify some distributions on a random variable. Okay. So again, if you remember what exactly is a random variable, so random variable is nothing but a variable which can take any random values, and the moment you say that the random variable x can take any random values, there has to be certain probabilities associated with certain values that x can take. So again, like I said, any random variable is denoted by either uppercase letters x, y or z, and then so again x can be either discrete or it can be continuous. So if x takes values which can be mapped to a set of integers, is called as discrete. Otherwise, on the other hand, if x can take any value in an interval or union of two disjoint intervals, then x is said to be a continuous random variable. Okay. So in this session we will spend some time on quantifying discrete random variables, and then this is exactly where, if you have heard about distributions like binomial, Poisson, hypergeometric, negative binomial, we will talk very briefly about these distributions. Okay. So again, the focus entirely in today's session would be entirely on discrete random variables, and then how do you sort of define certain distributions that x belongs to or x fits into. Now first you have to understand that what do you mean by a distribution. So distribution means that once you coin a random variable x, x actually follows some behavior, isn't it? I mean, since x is a random variable, x contains some probabilities or x is associated with certain probabilities. So I can actually say that x should follow a certain distribution. So in a way, distribution means nothing but x should follow some path or x should follow some behavior, alright, or x should show some properties. Okay. So this is exactly what we mean by when we say that x follows a binomial distribution or x follows a Poisson distribution, etc. Okay, so very first distribution we'll talk about is called as a very elementary one, rather Bernoulli random variable. You might have heard about Bernoulli. Now again, each and every distribution has its own properties or characteristics. Okay, so a binomial distribution or a Bernoulli distribution would be entirely different from Poisson. Poisson would be entirely different from some other discrete distribution, etc. By the way, in literature you have number of hundreds of different distributions. Okay, so even these days people are researching on finding out new distributions. So again, the whole idea of finding or researching about new distributions is that the moment you find a new distribution, it can be fitted to a slightly different real world data set. Okay, so ultimately the entire goal is to sort of find a distribution which best fits the practical data that you want to analyze. Anyway, so coming back to Bernoulli random variable, so how do you define a Bernoulli random variable? A random variable x is said to be a Bernoulli random variable if its PMF is given by these pointers. So firstly, just by looking at this entire PMF, can somebody tell me, or rather can you think in your mind that what values x can take? So here clearly x can only take two values, either 0 or 1 with certain probabilities. Okay, so probability that x takes a value 0 is 1 minus p, and probability that x takes a value 1 is nothing but p, and of course p has to be a fraction because p denotes the probability, so p belongs to 0 to 1. Okay. So again, if you want to write down or summarize, x can take two values, either 0 or 1 with certain probabilities. Probability x is 0 is 1 minus p as per our construction, and probability x is 1 is nothing but p. Okay. Now the moment you write down the PMF, by the way, this is nothing but the PMF, isn't it? I mean, why PMF? Because again, if you remember vaguely, PMF means probability x taking on some value x. Okay. Alright, so again, the moment you define a PMF, I can talk about expectation, variance, etc., etc. So again, if you remember the formula of expectation in case of discrete random variables was nothing but summation x into p of x over the entire range of x. So here the entire range of x means what? Values which x can take, only two, so 0 and 1. So you take the corresponding x value and multiply by the corresponding probability. So 1 into probability x equals 1 plus 0 into probability x equals 0, and ultimately you end up getting p here. Okay, so the average or the mean or the expected value of a Bernoulli random variable is nothing but P. Okay, so now the moment you discuss Bernoulli random variable, the next immediate extension would be called as binomial random variable, and very standard. It's kind of taught in every statistics lecture, etc., etc. So how do you define binomial? And then we'll see a small example as well. Okay. Now suppose you have n independent trials of an experiment. Okay, so n independent trials of an experiment. So firstly, what do you mean by that? So simple example, let's say you toss a coin. If you toss a coin once, you are performing the experiment simply once. Okay, but assume that you toss the coin 10 times. So these 10 times you're tossing a coin are called as 10 trials. Okay, so trial is nothing but repeating the experiment those many times. Okay, so here how many times are you repeating the experiment? You're repeating the experiment n times. Okay, so n independent trials, and each of which results in either a success with probability p or failure with probability 1 minus p. Okay, so again kind of similar to Bernoulli random variable, the only extension is in Bernoulli we only repeat the experiment once, while in binomial we repeat the experiment how many times? N times. Okay, but again the same construction. So the random variable x can either take two values, let's say 0 or 1, with certain probabilities. So again let's say 1 minus p here and then p there. By the way, these values 0 and 1 are coined as success and a failure. So probably 1 is called as a success here, because if you see the slide, it tells you that the probability of success is p, while the probability of failure is 1 minus p. So probably getting a value 0 is called as a failure, and getting a value 1 is called as a success. So again connecting the same with the same example of tossing a coin. So again let's say if you're repeating the experiment 10 times, so my n would be 10. And let's say if you're tossing a unbiased coin, so in that case my p has to be 0.5, okay, but getting a head could be a success and getting a tail could be a failure there. Okay, so now how do you define the random variable x? So far this is the construction of the experiment we have, okay, but now if x denotes the number of successes among n trials, just to repeat, if the random variable x, how are you defining it? So x denotes the number of successes out of n trials, okay, number of successes out of n trials. So x would follow a binomial distribution with parameters n comma p. So again linking this entire idea to the coin toss example, let's say if you toss the coin 10 times, so n would be 10. If you're tossing an unbiased coin, p would be 0.5. Now you have to find out how many heads you're getting out of 10 tosses, okay, and that value would be a random value, of course, okay, and then that is denoted by x. So my random variable x is nothing but number of heads you are getting out of 10 tosses. Okay. So number of heads out of 10 tosses. Okay. Now the moment you define the random variable x, can somebody tell me that what values x can take now? So what values can this x take? So if you pause the video and think for a second, you will understand that the values that x can take can lie between 0 to 10, isn't it? Because let's say if you're tossing a coin 10 times, then all of them could be tails, which means the number of heads is 0, or all of them could also be heads, then x could be 10. Okay, or of course x can take any intermediate value as well, 1, 2, 3, 4, 5, 6, etc., but it cannot exceed 10 and cannot be negative also. Make sense? So once you define a random variable, the immediate next thing is to define the range of x, and in this case it's 0, 1, 2 up to 10 in the coin toss example. So this is the range of x, and hence x is clearly a discrete random variable because this is a finite sequence that you have. Okay? Alright, so this is the crux of the matter as to how do you define a binomial, but now the more importantly, any distribution comes with its own PMF function, CDF function, expectation, variance, etc. Okay. So this is nothing but the PMF of a binomial distribution. So again it's slightly technical, and this is nothing but the combination, if you remember vaguely from one of the earlier sessions in this course, that this is given by n choose I. So in how many ways can you pick I items out of how many items? N items. Okay. And then p raised to the power I, 1 minus p raised to the power n minus I, and then my I can range from 0, 1, 2, 3, 4 up to n. So in general, if x follows a binomial distribution with these parameters n comma p, where n is the number of times you are repeating the experiment and p stands for the probability of success, okay, this is exactly how you define these. So n is the number of times you are repeating the experiment and p is the probability of success, then this is nothing but the PMF, and the range of x, values that x can take, lie between 0, 1, 2, 3, 4 up to n. So by the way, this is the formula. So this is a combination formula. So n choose I is nothing but n factorial divided by I factorial into n minus I factorial. Okay. Alright, now I can actually plot the PMF of a binomial distribution having these parameters. So 10, 0.5. So assume that you have a binomial distribution. So x is binomial where n is 10 and p is 0.5. So this is my n and then this is my p. And then just to tell you that how does the PMF look like. So again, remember what do you mean by PMF. So for each value ranging from 0 to 10, PMF means nothing but probability that x takes a value small x here. Okay. So for example, how much is the probability x takes a value 0, or how much is the probability x takes a value 5 or 6, etc. And here you clearly see that this is a perfectly symmetric kind of a PMF. So for smaller values like 0 or higher values like 10, so at both endpoints probabilities are small, and somewhere in between, let's say 4, 5, 6, probabilities are larger. Okay. So again, if you try to connect with the coin toss example, things would be kind of intuitive. So let's say if you're tossing a coin 10 times, then what is the probability that you'll get 0 heads? So getting 0 heads means what? All of them are tails. Okay. So should this probability be a high number or low number? So among 10 tosses of unbiased coin, so probability of heads and tails is equal 0.5, 0.5. What is the chance that all of the 10 tosses end up being either tails or heads? So these probabilities have to be very small, isn't it? And this is exactly what you see here. At the same time, probability is that you will get somewhere around 5 heads or 6 heads or 4 heads have to be a slightly higher number. Okay. So this is one example. Similarly, this could be another example, slightly skewed example. And why skewed? Because here the major difference is n is 10, but then p is not 0.5, it's 0.3. So probability of getting a head or getting a success is small, so 0.3. So if probability of getting a head is small, then having, so number of heads out of 10 tosses would take smaller values rather than larger values. So clearly you will see that higher probabilities correspond to smaller values of x, and lower probabilities correspond to larger values of x. So depending on n and p, the parameters n and p, the PMF plot can vary slightly. Alright, so lastly, I can actually find out the mean function of a binomial and the variance function of a binomial. So expectation of x when x is binomial np is given by n into p, so simple formula, whereas the variance of a binomial np is given by np into 1 minus p. Okay. So again, these two are important formulas to remember. So mean of binomial is np simply, and variance is nothing but n into p into 1 minus p. Okay, so we'll talk about a small example. So kind of a long example, but I'll try to elaborate the points there. So it's known that discs produced by a certain company will be defective with probability 0.01 independently of each other. So probability that any disc produced by a certain company will be defective with probability of 0.01. Now let's say that the company sells discs in packages of 10 and offers a money back guarantee that at most one of the 10 discs is defective. Okay. So let's say you buy a pack of discs, so each pack would contain 10 discs, and there is a money back guarantee that if you find out any disc being more than one being defective, then there will be a money back. Okay. So at most one is a guarantee by the seller that at most one defective you can find out, but any number of defective items more than one, they'll provide a money back. Okay. So hence the final question to be asked here is what proportion of packages is returned, or what proportion of packages is returned. Okay. So here this is a binomial problem. I'll tell you why exactly is binomial. So simply what we can do is we can find out the probability that a package will have to be replaced. And isn't this the probability you want to find out? Because like I said, any value bigger than 1 out of 10 discs, then the package has to be returned. Okay, and there will be a money back. Okay. So essentially you have to find out probability that x exceeds 1. Now this could be easily done using getting the PMF of a binomial. So again, finding probabilities is linked to either the PMF function or the PDF function of the random variable. Okay. So probability that x exceeds 1 is nothing but 1 minus probability that x takes a value 0 minus probability that x takes a value 1. Okay. Now here what exactly is the value of n, by the way? So value of n is nothing but 10, because how many discs do you have in a package? 10 discs, right? and probability that any disk would be defective is 0.01. So this is a classic example of binomial where x follows, let me write it down. So binomial where n is 10 and the small p is nothing but 0.01. Okay. So this is nothing but the PMF of this binomial, and I can easily find out, plug in all the values here in the PMF and get the answer. So finally 0.005 is the probability that the proportion of packages returned is nothing but 0.005. Okay, so now just an extension of the same example. So now assume that if someone buys 3 such packages, and again remember each package contains 10 disks. So then what is the probability that exactly one of them will be returned? Slightly different example, again I can sort of boil down into a binomial setting, and exactly n would be what now? So my n would be nothing but 3 now instead of 10. Okay. So again from the previous slide, once you fixate this probability 0.005, and then this 0.005 means what? So 0.005 is nothing but the probability that the package has to be returned. Okay. So keep this value in mind, and then coming back to an extension of the same problem. So now if someone buys 3 packages, so n is 3 there, what is the probability that exactly one of them will be returned? Okay. And shouldn't this be the PMF? So 3 choose 1, and then this is nothing but what? This is nothing but the probability that the package has to be returned from the last part, which is 0.005. So p to the power 1 and 1 minus p would be 0.995 raised to the power 3 minus 1, which is 2. Alright, so ultimately the final answer comes out to be 0.015. Okay. So this is exactly how you can solve some binomial problems. I mean, understanding what is n, understanding what is p, writing down the PMF, and then once you have the PMF in place, once you plug in all the values of n and p, I can easily express any PMF or sums of individual PMFs as certain probabilities. Okay, so on the other hand, the next important random variable which is again a standard random variable is called a Poisson random variable. So name is different. The earlier one was, we started with Bernoulli, then we talked about binomial, and now the next one is Poisson. So now when do you say that x follows a Poisson distribution? So a random variable x taking value 0, 1, 2, 3, 4 up to infinity, there is no upper bound here, is said to be a Poisson random variable parameter lambda. So again any Poisson random variable depends on one parameter, which is lambda, if its PMF is given by this function. So probability x equals any value I, again slightly mathematical, technical, is nothing but e to the power minus lambda, lambda raised to the power I divided by I factorial. Again I completely understand that this is a mathematical expression, but nevertheless what this entire expression gives you, it sort of gives you the probability that the random variable or the Poisson random variable x takes on a value small I. Okay. But now again more importantly, you should understand that in what situations can you apply a Poisson distribution, or under what examples can you actually apply a Poisson distribution to model the data. Alright. So in fact a Poisson distribution is used widely to model any count data. So what do you mean by count data? So count data means number of something. So number of insects in a field, number of telephone calls in a day. For example, all these are examples. Number of road accidents in a month, right? So these are typical data sets or typical practical examples where a Poisson distribution might be a good fit to the practical data. Okay. Now again couple of things. So Poisson distribution, its construction, PMF is entirely different from binomial, as well as applications where one can apply binomial vis-a-vis a Poisson are entirely different. So firstly, the major difference is what values can a Poisson random variable x take? 0, 1, 2, 3, 4 up to infinity. So there is no upper bound there. Whereas again if you go back to binomial setting, the values which a binomial random variable x can take has to lie between 0, 1, 2, 3, 4 up to n. Okay. And there the entire experiment was different, right? If you remember, you had n, which is number of trials, then p is probability of success. Whereas here it's entirely dependent on a single parameter lambda. Okay. And then applications are also kind of very specific. So if you want to model or if you want to fit number of something, so number of insects, number of telephone calls, number of accidents, number of COVID cases in a day or in a week, okay. So number of anything is called as count data, and any count data could be suitably modeled using a Poisson random variable. Okay, so again Poisson PMF plot, this is exactly how a Poisson PMF plot looks like. By the way, this is a PMF plot with parameter lambda being 4, alright, parameter lambda being 4. Alright. Yeah, by the way, this entire parameter lambda under a Poisson distribution, if you see, if you try to find out the mean of a Poisson variable, it's nothing but lambda. Okay, so hence this lambda is nothing but, let me write it down. So lambda is called as average count or the mean count. So again, if you go back a couple of slides, in all these examples we saw, so what would be lambda for the first example? So lambda for the first example would be the average number of telephone calls one receives in a day, or the average number of insects in a field, or average number of road accidents in a month. Okay, so this is exactly what is meant by lambda there. And again, if you go back to the PMF plot, so since my lambda is 4, so I know that the average number of occurrences is 4, so you should see a higher peak around 4, isn't it? Because average is 4. And as in how you will go down the line away from 4, the probabilities start reducing there. Alright. Okay, so coming back to this slide, so mean is lambda, whereas variance surprisingly is also lambda. Okay. Thus, the mean and variance of a Poisson distribution are exactly same, equal to lambda, and this is a very classic example of something which is called as equidispersed distribution. So equidispersed means what? So mean and variance are exactly equal. So equidispersed. So the location is same or the mean is same as well as the variance is also same. Okay, so again a small example, suppose that the average number of accidents occurring weekly on a particular stretch of a highway equals 3. So the moment if somebody tells you the average number of accidents, firstly number of accidents, so number of accidents, it should immediately come to your mind that Poisson might be a suitable choice here. And what exactly is that average? Average equals 3, so my lambda has to be 3 immediately if you are fitting a Poisson distribution. And now the question is that what is the probability that there will be at least one accident this week? Okay, so what is the probability that there would be at least one accident this week? So here clearly let me define my x to be the number of accidents occurring on that stretch of highway during the week, and then where lambda is 3, and then you want to find out probability that there is at least one accident this week, which means nothing but this probability, isn't it? So at least one means what? So at least one means bigger than equal to 1. Okay. By the way, you have to be kind of familiar with all these terminologies. So at least, at most. Okay, so at most means what? So at most means less than 1, or rather less than equal to 1 if you have a discrete random variable. Okay. Anyways, but then at least means 1, 2, 3, 4 or any number above. So we have to find out probability that x is bigger than equal to 1. And again a typical way to handle this is doing 1 minus probability that x is 0. So firstly, why do you think we are doing it this way? Because remember that at least there is no upper bound, right? I mean, one cannot simply keep on adding the PMFs from 1, 2, 3, 4, 5 up to infinity, isn't it? So a better way to handle this is to take probability that x is 0 and subtract that from 1, alright. And then for, like I said, for finding any probabilities you have to again make use of the PMF. So ultimately this is the PMF, and then you do 1 minus that. So e to the power minus 3, 3 to the power 0 divided by 0 factorial, 0 factorial is 1. So ultimately it reduces to 1 minus e to the power minus 3, which is nothing but 0.95. Okay. So probability that there will be at least one accident this week is nothing but 0.95. Okay. Okay. Another example, let's say if the average number of claims handled daily by an insurance company is 5, okay, what proportion of days have less than 3 claims? Again a classic Poisson example. So it tells you in the very beginning that the average number of claims is how much? Is 5. So immediately my lambda is nothing but 5. And then you have to find out that what proportion of days have less than 3 claims. Okay. So here let me coin the random variable to be nothing but the number of claims on a particular day where lambda is 5, and then less than 3 claims mean what? So probability that x is less than equal to 3. By the way, a small typo here, that less than 3 means what? Less than 3 means strictly less than 3. Okay. So this should be rather probability that x is less than 3 and not less than equal to. So please change that. So probability x is strictly less than 3 is nothing but 0 plus 1 plus 2. Okay. So such a probability where you have less than or less than equal to could be easily handled. If you have more than or more than equal to, the correct way to do it is 1 minus something. Anyways, but then these are the individual probabilities, and then you take help of the PMFs and simply feed in the values. So this is the PMF where x is 0, lambda is 5. This is the PMF where x is 1, lambda is 5, and this is the PMF where x is 2 and lambda is 5. So ultimately the final answer reduces to 37 by 2 into e to the power minus 1, which is nothing but 0.1247. Okay. Okay, so now very briefly we'll talk about a couple of other discrete distributions to end this session. So along with binomial, Bernoulli or Poisson, you have a number of other interesting distributions. The very first one, let's say, is geometric distribution. So what do you mean by a geometric distribution? Let x denote the number of failures before the first success. Okay. So in the beginning itself, geometric distribution, how you define a geometric random variable is entirely different from, let's say, binomial even or Poisson, etc. So now let x denote the number of failures before the first success. So again, just a simple example, let's say again you're tossing a coin 10 times, okay, tossing a coin 10 times. So a geometric random variable would be number of tails before you see the first head out of 10 tosses, okay, number of tails before you see the first head. Then x follows a geometric distribution with parameter p, where p is nothing but probability of success. Okay. So again, if you go back to binomial, how did you define binomial? So binomial means nothing but number of successes out of n trials, whereas in geometric slightly different. So x is nothing but number of failures before the first success, and this would be nothing but the PMF. So 1 minus p to the power k into p, and this gives you nothing but probability that the random variable x takes the value k. Okay. And lastly, a slightly different distribution called as negative binomial distribution. So again, the definition itself is slightly different. So here the x is defined by the number of failures before the rth success. So again, if you remember what was geometric, so geometric was number of failures before the first success, and negative binomial is an extension of geometric in a way, where x is defined by the number of failures before the rth success. So again, for the coin toss example, let me fix some values. N is 10, r is 2. So in this context, a negative binomial random variable would be defined by number of tails before I get 2 heads or before I get the second head. Okay. So this is slightly different from geometric. In geometric, we had a number of tails before the first head, whereas here number of tails before certain rth head. So let's say if r is 2, it will be second head. Okay. And again, this is an entirely technical PMF of a negative binomial distribution. Again, this gives you probability that x takes a value small k, and again this is a combination idea. So k plus r minus 1 choose k. Okay. So k plus r minus 1 choose k. Through this entire session, we are kind of slightly more comfortable to sort of define discrete random variables. By the way, Bernoulli, binomial, Poisson, geometric and negative binomial are examples of discrete random variables where x can either take value in a finite sequence or infinite sequence, but value has to be discrete. And then we saw a couple of examples as to how do you find out probabilities using PMF, then what is the expectation, what is the variance, etc. Okay. Now immediately in the next session, we will spend some time on describing continuous distribution. So a very useful or a standard distribution there would be normal distribution, of course along with couple of other distributions as well. Okay. Thank you.